Cool. Well, welcome, Cy, you said. So I'm Austin Wilson, so we're with Olympus Controls, Jonathan Salazar. So we'll be talking about machine tending, so how to work with a robot and tend a machine.
A little bit of background about us. So my name is Jonathan Salazar, Olympus Controls. I am the robotics solution engineer. A little bit about me, I graduated from University of North Texas in 2018 with my mechanical engineering degree and kind of hit the ground running with automation. I did my capstone project, I did my internship, and first job all with kind of the UR robots and automation things. So got about 7 years of experience at this point and been with Olympus now for about 4 years.
I'm Austin, like I mentioned. I am an applications engineer with Olympus, so I focus on technical installs, technical support for our customers and our sales team. Been with automation working for about 6 years now and got my bachelor's in electrical engineering technology.
A little bit about our company background. So we work for Olympus Controls. Olympus Controls was founded in 1998, kind of in the Northwest area near Portland, Oregon. A little bit about us, we're a high-tech automation distributor, and so we focus a lot on like motion controls, machine vision, now recently robotics. But we're also diving into the more engineering solutions. We have a whole team dedicated to just doing custom builds from the ground up, from simple things like simple robot mounts to custom enclosures, all the way up to like, in a custom autonomous vehicle robot. So kind of all in-house powerhouse. We've been with UR robots for about 12 years now. Hit up pretty strong with them. And now, plus or minus one, we're the largest UR distributor in North America for the universal robots. UR robots, founded in 2007. And they are now the #1 collaborative robot supplier in the world. So they kind of coined that Cobot term and did a lot to push the idea of that collaborative robot, not just the traditional industrial robot, but more of a approachable, ease of use, easy programming kind of robot.
And this is kind of their product line of all the robots that UR has. So they go as small as these robots here with the 3E. So the number you see on the board there, that's their model, and also the payload for the robot. So 3 is 3 kilograms, so about 7 pounds is what it can pick up. And then it goes all the way up to 30, or actually 35 kilograms, so over 70 pounds is what that highest end robot can pick up. So have a lot of different offerings, a lot of different reaches as well. So if you need to have a longer robot, they have a new long robot right there. So yeah, plenty of offerings.
Rule of thumb is the bigger number, the bigger reach of the robot, bigger payloads. A couple of discrepancies, like we said, the 8 is a little bit less payload, but longer than the 16 and 12. But rule of thumb is bigger number, bigger payload for sure, usually bigger reach. The sweet spot for machine tending is usually around like that 12E range to like the 20, depending on part size. That's a good reach for reaching multiple machines to and from your work area and picking up the heavy parts with tooling.
And then this is kind of a quick guideline for different steps to think about and what to consider if you're doing any type of collaborative robot install, not just machine tending, so like your throughput, the reach and the payload of the robot, parts and presentation, that's a really big one. And not enough people focus on it is because with all automation, we really want our parts to be oriented and fixed the same way every time. So the robots, they're going to go to the same place every time. So if you can make sure your parts are in the same place every time, we'll be solid. But they really don't like variation. So if you can get rid of all your variables and movement in the system, that'll really help you out a lot. Collaboration, you have to consider how it will work with humans. Connectivity and integration, so I'll talk a little bit about that later in another slide, but you really just need to think about how it's going to interface to your machine, and there's a few different ways of doing that. Grippers and end effectors, so Jonathan will talk about that a little later, but we have a bunch of different options between concentric grippers, 2-finger grippers, vacuum, suction cups. We we have this little magnetic gripper here for ferrous material parts. And so that's another consideration. We have mounting, fencing. So these are collaborative robots, so you normally don't really need fencing for them because they will stop if they hit someone. So you're kind of more standard, like what you'd imagine a really heavy-duty robot. Those usually do need fencing because they can crush people. They can be very dangerous. And yeah, that's pretty much it. Environment as well. So their newer robots are IP65 rated, so they're waterproof. So that's pretty cool.
Keep in mind it is an IP rating, so it is water testing. Yeah. Sometimes cutting fluid is a little bit more viscous than water. It can be a little bit tougher than typical IP ratings, but keep in mind there are options. You can add like a suit on top of it or some kind of waterproofing ponchos to ease with that. Or my slide. Okay, so the 3 questions you should ask when dealing with machine tending is like, what kind of material are you dealing with? So what is the material? How many variations of parts are you dealing with? And then how is the part being presented? Those 2 things will kind of guide you in tooling options and then part presentations, any kind of external equipment needed for the application. So first bullet here is where's the material coming from? This is ranked from easiest to kind of a hard part presentation. Easiest would be the robot's not dealing with it. If it's a bar feeder inside the lathe machine, the parts fit automatically. The robot just deals with the outfeed machine part, gripping it, placing it in the finished pile. Next up, for easy, would be some kind of singulation or some kind of pattern for you to take advantage of. Maybe the parts are stacked up on a table in a certain array, or it could be even something simple, like the example here, kind of a gravity feed system that feeds the part up to the same pickup position every single time. This is kind of the options. Correct. Gravity fed like round stock, for example. I guess they're both round stock, but typically gravity fed's good for round stock, kind of a lathe machine tending, as long as you can account for all the part sizes. And then the palette or templates is more for like square parts, square blanks. Next up in difficulty would be kind of this medium example of maybe you're picking parts off a conveyor. That usually means coming off some kind of upstream process, and you have to kind of account for some of the variation of the parts. They could be upside down, they could be kind of skewed on that conveyor. Assuming we're flat, we can do something like a 2D vision system, or even some kind of mechanical guidance or fixturing for the parts. So the camera is integrated with the robot? Correct. So Universal Robot is a brand just as the ARM, and they open up their software to be open source. So a lot of third parties have come in and designed custom toolings, as Austin kind of touched on. And so all these tools are not UR tools, they're kind of a third-party brand. Robotique, On-Robot examples, Zimmer. And so a lot of different ones have different 2D cameras that are nice and plug and play. They got a specific software, you upload the UR cap to the robot, and it's nice and plug and play. Tested and vetted by UR too. So that's kind of the 2D vision example. And then the hard level, the one that's most difficult, would be some kind of like random picking. Maybe the parts are on a conveyor, but they're all stacked up and skewed. So typically some kind of bin picking system. What you can do there is some kind of 3D bin picking software and camera to account for that, or maybe even something like a vibratory bowl feeder to kind of help stage up those parts. But that is going to add the most complexity to your programming, more cycle time, and more cost. Well, that's expensive. So we do try and do the below options first before we get to that point. Other things to consider for your application: how much time do you need before operator intervention? So again, how much time do you need for the robot to run before operator comes back in there and adds parts, restages the parts for you? Typically, we could do this by how long is a shift for the operator? How many parts per shift? Okay, maybe you want to run 2 shifts. Okay, that kind of details, influences your work area, how much parts you need per setup, or how big your work area is supposed to be. It can also affect how big your robot is, how much reach you need to get all those parts. Next bullet here, where do the finished parts go? Again, just thinking whole picture. After the parts machine from your CNC machine, where do you place it? It could be something simple, like back on an accumulator, a single drop-off point and the conveyor just queues it up. Or something simple like some kind of bin for the good parts. Depends on the part as well. If it's delicate, you don't want to drop it in a bin, you want some kind of nice placement. It could even be putting it back on the pallet you just picked from, putting the finished part back on that same pallet for the tender. And then, of course, rule of thumb is the 3 things we strive for machine tending for the parts is nice part consistency, meaning like part to part, they're going to be the same size and same shape. part to part. You can run multiple size parts, that's fine, but part to part you want kind of similarity. The example we give is, think of your own arm as the robot arm. You're very repeatable, so you can come back to the same spot within 0.01 millimeters over and over again. But you're blindfolded, you have an oven mitt on, and you have a pair of tongs as your tool. So you don't have the ease of use of vision or force field to pick up parts. So if something changes, if your part's different shaped or it moves, you have no way of accounting for that. So you need kind of extra things involved. The robots do have a built-in force sensor. We can take advantage of that to kind of do a force field and touch off, but it does add cycle time. So added tools, added costs, added time. So along that same topic, limit variations and things shifting. Make sure everything's nice and rigidly bolted down. You have some guide pins for your fixtures. That way when things come back in, it'll be in the same spot every single time. And if possible, singulate parts. Make it easy. One single pickup position. Okay, so what kind of gripper do we need? A lot of different options. We've covered a few here. Quick crash course, going from cheapest up to more complicated, more expensive. Simplest gripper would be something like a pneumatic gripper, shown here in the bottom left. That's going to be a lot faster and a lot more cost effective than an electronic one. A little bit of complexity in the programming side. You got to set up your own like pneumatic cylinder and IOs to kind of control it, but overall a lot cheaper. One step up would be something like a simple electric gripper. They might have a UR-Cap mentioned software, or it might not. It could be just IO settings on off. But this will give you a little bit more position feedback, a little bit more options, and possibility of a UR-Cap. Kind of in between there is the concentric gripper, so bottom right. That one is more for round parts. 3-finger jaws that kind of close in. That's great for any kind of like round stock you might be picking up for lathe machine tending or so. Those can be either pneumatic or electric. And the top tier would be something like an adaptive gripper. A couple different brands. The ones we use a lot is the On-Robot and the Robotique. These are more advanced adaptive grippers. The benefit is you have the full access to the stroke, the speed, and the force. And they are collaborative, so they're not going to hurt the human being. It'll give you a little bit of a pinch, but it won't hurt you. They do come off the shelf with nice mounts and a nice even IO coupler, so you can bolt right to the end of the robot wrist, as shown here. So you limit a lot of that need for cable management, running tubes or pneumatic lines all the way across. It's right at the end of the robot. And along with that same thing, dual gripper, that can be any of these above mentioned options. It's just doing 2 grippers instead of 1. If you think about it, that can help your cycle time immensely. The process normally is you open up the CNC machine, you'll pick up your finished parts, drop it into the finished part pile, come back over, pick up a new blank, and load it into the machine. That's a long process. If you have 2 hands, you can pick up a finished blank, open the door, go in, pick up finished part, go ahead and drop off the new part, and then come out. You save half the time of coming in and out of the machine. So big benefit for machine tending, very common. Along that same subject, we'll stay on with a real case study. This is one of our customers out of Tulsa, Oklahoma called McElroy. They are an in-house OEM manufacturer. They do things for like spline tubes. They basically add the tube thinning on the end of metal tubes. But they manufacture a lot of their machines in-house. And so they got a bunch of CNC machines, and they're doing a lot by hand. There's no automation besides the CNC machine, and they're looking to automate, kind of get their feet wet with it. They approached us looking for a universal robot, a Cobot. They were interested in ease of use, no need for other caging or safety equipment, and something they could redeploy different machines if needed. So kind of a redeployable robots. They did ask for a full turnkey solution, so they wanted everything. They wanted the mobile stand, the cobots, any kind of tooling, any kind of custom grippers, part presentation fixturing, and help on site with deployments. The parts they were running, there was 2 size parts. They were aluminum blanks, so low aluminum rectangles, 3/8 inch thick, and the sizes were 3x4 inch and 4x6 inch. So we need one tool to kind of pick up both parts. But they were simple shapes, rectangles, nice, easy to pick up from. So right off the back, a couple of things we can get off the shelf. So for example, the UR10E robot's our choice. Again, that's kind of the sweet spot. It's a good reach for the robot, for the application, and good payload to pick up your custom tooling and the light parts. For gripper, we went with a pneumatic gripper. They were kind of cost conscious, so we said pneumatic would be a little bit cheaper. It'll give us enough force and speed to pick up these parts fast. One thing we haven't mentioned is we went with a custom kind of fingertip design on one of them called the swivel fingers. Right. So with the machining process, there was a 3-stage process, 3 devices inside the CNC machine. Going from stage 1 to stage 2, it required you to flip the part upside down. Typically, that requires you to actually drop off the part on a fixture and have the robot come around and pick up the part upside down to achieve that pick position. They were worried about cycle time, and so we found this nice solution from our supplier, Zimmer, that had a pneumatic flipper finger. And so in hand, when gripping the part, it would automatically flip the part around 180 for you in hand. So we tried that. We did want a dual gripper mount, but there was no off-the-shelf option for that, so we had to design a custom dual gripper mount. And then they also kind of wanted a custom mobile table for a specific size. They wanted, I believe, 2 shifts worth of parts. And so it gives the part size. We kind of figured around that. So here was the customization parts. I took care of designing all the custom things. So here was my design for the mobile table for the robots. Kind of a simple electrician design. On the top, we did fit it up with breadboards. If you don't know, breadboards are kind of machine plates that got predefined spacing for threaded inserts. And so the benefit there is we can use something simple, like some thread rods, to kind of fixture the parts and make a nice array for the robot to pick from. Again, going back to that kind of easy application, we're picking up from a predefined grid of parts every single time. And you can stack them up higher. So I believe it was up to about 5 layers of parts, is that correct? 4 or 5?
I think we did more.
More than that?
Did like 10.
Yeah. So based on the reach of the robot, we kind of spec'd up the table, and then based on the amount of parts, it kind of drove the design for that table. Pretty simple in that, aluminum extrusion frame, a machine base plate for the control box and other things, and a breadboard on top, like we said. On the tooling side, like we said, the grippers were off the shelf and the fingers were off the shelf for the tool, but everything else had to be custom. So I did design this custom 2 gripper mount in 2 pieces, kind of a top and a bottom half of it. The benefit there was just for ease of assembly. You can bolt the grippers onto the top part of that assembly, bolt the bottom to the robot, and then combine both after the end. Plenty of space too for cable management. It's going to be a lot of tubing coming across here, all pneumatic. And shown here too is the custom swivel fingers, made a little custom kind of nubs to pick up the parts, and then some simple custom fingers for the other part. They were flat parts, so fingertips was pretty simple, just flat parts to scrap onto from. We did see that, yeah, we saw some slippage. Even though it was nice contacts, if there's any raised parts of the flat part, it would kind of pivot on it. So do points of contact to make it kind of pivot. And so the solution there was to kind of machine a little groove on the end of the fingers, kind of a flat slot that we can actually bottom out and have 3 points of contact instead of just 2.
I believe they did end up knurling the edges of the fingers a little bit too,
okay,
to give it a little more grip.
More grip, yeah. After everything was designed in CAD, I did throw into a robot simulation software just to verify no problems with reach, nothing was binding up or singulators for the robot. It all looked pretty good. And so we got to fabricating. We did try and make everything in-house as much as possible. I did go and cut the extrusion and tap all the ends and assemble it in-house. Everything machined, though, we did outsource. We do have a local machine shop at our Kent office counterparts, and we machine some of the stuff with him or just off the local suppliers for machine shops. So breadboards, of course, bought out, the bottom machine plate bought out, all the extrusion we had in-house and we cut and fabricated in. And here's what the dual gripper ended up looking like. Very similar to the concepts. Again, the custom fingers, flat fingers, and then on the other side, the swivel fingers.
Cool. Oh no, what happened? There we go. Cool, cool. Yeah, so I went on site to help install the machine. So generally what we recommend is to dedicate downtime for the machine, make sure you have, if it is running parts, have those parts running on a different machine. Generally the install can take up to a few days, depending on the complexity of the application, maybe how difficult it is to get the parts into the machine with the robot, other factors like we mentioned before on like how well the parts are fitting onto the fixture. If they're very fixed and not moving around, then that's gonna make a quicker install in the long run. So generally, most of the time on site is just gonna be programming the robot, which, like I said, could be a couple days. We have done some installs where just only one day was needed on some very simple parts, where we're just picking all the parts from a fixed point, and then the conveyor is just bringing the parts down to that fixed point, and then we're just loading that part in the machine, and then taking it out and dropping it off again at a fixed point. Also, when we come on site, usually we'll recommend shops to have other resources available to us. So concrete anchors is a big one. We want to make sure that the fixture going up to the machine is secure and that it won't move or walk over time. So having someone on site to help with concrete anchors or to show us where to put the concrete anchors, that will help a ton. And also just having a mechanical shop resource available if that shop wants to design new fingers of their own. That's a big benefit to that shop, because then they don't have to contact us for new designs, and it'll save them money in the long run. And then also just having a CNC programmer on site who knows the machine, who's able to run the CNC program so we can test parts at the final step once the robot is programmed, and then that'll just make the process much more seamless. Okay. All right. And then the last thing is training. So we recommend to have at least 2 people trained on site with the robot. This is just to prevent, in case the one person who knows the robot leaves, then you lost all your knowledge. So we like recommending at least 2 people to know it. And usually we'll focus on training on site as well, just showing them the pendant and how to teach some points and some basic error recovery. And then if someone wants to really own it and create their own programs from scratch in the future, we also have some training that we provide at our office as well. Okay, so how do we talk to the machine? So we have our nice cell, we have our table, we have the robot on it, and then we have the machine right next to the robot. So how do we get the communications from the robot to the machine? So there's a few different options. So the most basic and simple is usually just a simple digital input or digital output from the robot to the machine. A lot of machines have what's called an in-thin signal, which is basically just a configurable signal that the machine can set up, and it's looking for some signal from the robot. So again, that's very simple. Also, there's plenty of industrial protocols that are over Ethernet. So EIP is a very common one. Modbus is also another common one. And then there's also third-party systems that handle all that integration for you and handle that communication. So in this install that we're talking about with this case study, we actually used one of those third-party systems called VersaBuilt, and that handled the communication from the robot to the machine. It allowed the robot to call specific programs from the machine and I/O as well to turn on outputs. And the nice thing about that is it also gave a pretty sleek interface on the robot as well.
Different programs can be installed on the robot?
Mm-hmm. Yep.
Correct. So like I said, UR just focuses on the arm, and then third parties develop these softwares or plugins for it. Think like an app on your phone. And so yeah, at least a bit better interface for dealing with the robots.
And then also, if y'all need help talking to the machine, there's plenty of online resources and examples as well. So hopefully this video loads. Maybe. It doesn't look like it's loading anyway. Okay. Huh? Yeah, it's trying to go to YouTube. Ah, darn. Oh well. Yeah, we have a video example next. But yes, there are plenty. Okay, yeah, there we go. So this is a video showing our actual application on site once we got it all working.
Your reading station.
Yeah, so they added a repick station because they added grooves to those flat fingers, and the repick station just made sure the part was inside the groove there to keep the part flat, so the part didn't tilt in the fingers.
Part going from stage 1 to stage 2. See here in motion once it picks up. We'll flip it right here. Flip. Clean up the vise. Drop off the new blank. Put a force in the back. Square it off.
Yep. Yeah, that's it.